So here's my two-dimensional model of a four-dimensional universe. It does seem to put into place all of the things that we know quite well, and it does seem to have a bit of insight. So here we go. First of all, this is a sphere. Obviously, I can only draw a circle, so picture this as a sphere. And this is now, right here, the surface. Okay, so it's three-dimensional like our universe. Yeah. So where is time? Okay, well, time travels this way. Okay, so right here is the Big Bang in the middle. We can only look into the past, into the back to the Big Bang. We can see inflation, we can see galaxies, etc., etc. Okay, we could never see our now slice except for where we are. Okay, so that's the direction of time. This surface is space. Okay, and obviously everything's expanding. So this surface is getting bigger and bigger as the sphere gets bigger. So now you can see where dark energy comes from. It's the expansion of the sphere. So dark energy is either the accumulation of past time, or the universe is expanding. Or you can say the other way, is that the expansion of dark energy is causing more time to accumulate. It's chicken and egg, obviously. So this model, we can see a few things. First of all, if we zoom in on the surface, now we can see GR, or Einstein's gravity, right? The surface isn't going to be smooth. It's going to be dimples like this. You can think of the trampoline analogy, obviously, the easy one. The larger things are, so we have big stars here and stuff, the more resilient it is to the expansion of time. Okay, because the past is pushing us this way into the future. Here you go. These are all more resilient. Your little particles are here. We're somewhere in the middle there. There you go. Well, you've heard the analogy that things don't fall to Earth. The Earth moves up to everything. That explains it very nicely. It's time that's pushing everything. All right, so there you go with your gravity. Entropy, well, that's pretty logical with this model. Everything's getting bigger and bigger and bigger. Right in the middle is a super hot, dense. Out here it gets cooler and cooler as we go. The surface keeps getting bigger and bigger, and the bigger the surface gets, the more places the energy in here can go. So of course that's going to increase entropy and make the universe cooler. Special relativity, well, it's pretty logical in this, with this idea. We can use the lightning hitting the train thing. So here you have a slice. Here you have an observer moving this way. You have the lightning strikes here and here, equal distance. In a future state, he's going to travel down to here, and eventually he's going to meet this lightning strike. Well, and this lightning strike's traveling up to it as well. This one's traveling there. Boom, they're going to meet there, and then in a later slice, this one will eventually hit him as well. Special relativity is pretty easy to see in this dynamic. All right, so now we can get into quantum mechanics. This is where it gets interesting. So here's our now slice. Here's the Big Bang. We can only look into the past. Okay? We are traveling into the future, facing backwards, never knowing what's behind us in the future. So we can see all the particles in here, yada, yada, yada. And we can make predictions in here easily. So we can see a galaxy right over here, back in time, 100 million light years away, whatever. And we can predict its path into the future, but only pretty much till the now slice. Where it is now in the universe, we can probably predict, but eventually it's going to have a wave function into the future. So this is the predictable past made of particles, general relativity, and this is some sort of probability field or whatever you want to call it, but it's the future. Yeah, so even large objects have a probability wave. It's just very far into the future. I mean, in order to know where everything is here, we're going to need an infinite amount. There's going to be an infinite amount of variables as we go. Okay, so QM's in the past. QM's in the future. General relativity is in the past. That's why we have problem. That's why it's different math. They're different things. Okay. This now slice is expanding into this probability field, and all it is littered with wave function collapses. Every Planck time shares a wave function collapse of everything it sees. So it's expanding, collapse, 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 collapse as it expands. We can never see our own slice, okay, because of causality. And the speed of causality, light speed can only get to you at a certain speed. So you never see your slice, okay, ever. Now, if we zoom in on the now slice, this is what we see as, and we try to stop looking into the past and start looking at the slice. This is where what we measure as QFT. Okay, this is where all that stuff seems to happen. When we start to look into the future, this is when all the wave functions and probabilities start to exist. So how does this explain something like quantum entanglement? So we're on a slice, just entangled two particles, but they're just above the now slice. They're unobserved yet. Okay, only once they're observed do they come into the now slice. So we start to separate them. We're taking one this way. Oh, sorry, this should be in the future right there, a little bit in the future, but they're still connected through the past. Let me see. But they're always just ahead of the now slice as they're going. So once we observe one, it comes onto the now slice. This one will come into the now slice, and we can infer what it is through the knowledge of the past. In order to double check it, we'd have to bring it back into a future slice to check, but all the time accumulating time to do that while it was in the future slice. Okay, so there you go. Pretty much explains everything. Yeah, there it is.